Here is example 2 for optimization. Find two numbers whose sum is 20 and whose product is as large as possible. Well, consider two numbers, x and y. We know that their sum is 20, so x plus y is equal to 20. We are asked to optimize the product. We want to maximize the product, so that's what we're optimizing. So we have some function p, which is our product of x and y, and it's equal to x times y, because that's the product of x and y. Now we can use x plus y equals 20 to be able to solve for one of our variables, because we're not allowed to really take the derivative yet, because this is first level calculus. Take the derivative with respect to two variables. So y is equal to 20 minus x. That means that I can substitute 20 minus x into y and make this function in terms of x. So p of x is equal to x times 20 minus x. This is my product function. Furthermore, p of x is equal to 20x minus x squared. Now, to maximize the product, we have to find the derivative and find out where these critical points are. My product function, p of x, is the model. So that's the hardest part, is finding that model. Now we have to actually do our first derivative analysis. So here we go. P prime of x is equal to 20 minus 2x. This always exists, so we'll set it equal to 0. So negative 2x is equal to negative 20, and therefore x is equal to positive 10. Now this could be a min, and this could be a max. So we need to actually double check to make sure that this is, in fact, a relative maximum. So here is my line analysis for p prime. If I look to the left of 10, p prime is going to be positive. If I look to the right of 10, p prime is going to be negative. Well, because p prime is changing from positive to negative, this is indeed a max. So I know that x is equal to 10, and I know that y is equal to 20 minus x, and since x is equal to 10, that means that 20 minus 10, that's just 10. So x is 10, y is 10, that means that my maximum product is 100, and that is the solution. This is optimization example number 3. A rectangle has its base on the x-axis and its upper two vertices on the parabola y equals 12 minus x squared. What is the largest area the rectangle can have, and what are its dimensions? Here is my rectangle inscribed inside of 12 minus x squared. If you look at one of the vertices right there, let's call that x. From 0, the distance is x. The height of our rectangle is f of x, since it's inscribed inside of 12 minus x squared, and that height is the actual function value at x, which is 12 minus x squared. Furthermore, the length of this rectangle is 2 times x, because that only gave us half of our rectangle, that one x part. And we know that y equals 12 minus x squared is symmetric about the y-axis. So we have our length of our rectangle, 2x, and the height of our rectangle, 12 minus x squared. Therefore, we have the area of our rectangle in terms of x, which is length, 2x, times the height, 12 minus x squared. This is my model. Here is the model for the area. That's the hardest part. It's done. Let's distribute the 2x. Here we have 24x minus 2x cubed. Once we have our model, it is time to actually optimize. Optimization is to find where our max is, our maximum area. To figure that out, we take the derivative and find our critical points. The derivative is 24 minus 6x squared. Since this always exists, we'll just set it equal to 0. We'll subtract 24 from both sides, so negative 6x squared is equal to negative 24. Divide both sides by negative 6, x squared is equal to positive 4. Therefore, we have critical points at x equals plus or minus 2. Because we have 2 critical points, and actually always, we have to do our line analysis in order to ensure that we have a relative maximum. So here's the graph of a prime, the derivative of our area. Let's look to the left of -2. Let's try -3. -3 squared is positive 9. 24 minus 54, well, that's going to be really quite negative. So we have a negative number to the left of -2. If we check in between -2 and 2, say 0, 24 minus 0, that's positive. If we look to the right of 2, say 3, we have 24 minus 54, that's still negative. Therefore, we have a local minimum at x equals -2 and a local maximum at x equals 2. X equals 2 is what we're looking for, since that actually maximizes my area. So we have a local maximum at x equals 2, and that's what we're looking for because we want to maximize the area of this rectangle. Let's take a look at our graph and see what this means. At x equals 2, that means that our other vertex is at -2, and the length of this rectangle is 4. F of 2 is 12 minus 2 squared. That's 12 minus 4, that gives us 8. So that means that our height is 8. This is a maximum area of 32. So graphically, we can look at it that way. Let's take a look at it analytically. If we didn't have a graph per se, we could say that the largest area is found at A of 2. That means that we just have to plug 2 into my area. My area is 2x times 24 minus x squared, or we can distribute that. (24 times 2 is 48. 2 cubed is 8 times -2 is -16. 48 minus 16 is 32. Here is the analytic way of finding the maximum area, just by plugging our maximum x value into the model that we created. Now let's look at the dimensions. Let's call the width, the actual function value, that height-ish thing, 12 minus x squared. Well, if our x is 2, that's 12 minus 2 squared. That gives us 8. And our height, or let's call it the length even, is 2 times x. Well, 2 times 2, that gives us 4. Thank you for watching.